Okay, now that we've learned about moments and we learned about cross products, now we can combine the two. And this is where this approach really shines, because now we can calculate our moments, which again, it can be we can think of these as a vector in a direction mutually perpendicular or perpendicular to both of the vectors that we cross. So if that's the case, we can take a position vector and we can cross it with our force and get a moment. And what I mean by that is if you have some point O along some line, well, let's say it this way. You have a point O in a plane. Let's say we have a UV plane. This could be the XY plane or anything, but let's just call it the UV plane right now to be real general. And in this plane is some force acting. And there's a couple reasons I don't like that force. First off, let's actually make it an arrow. And let's move it further away. So let's say it's acting like this. So I'll put a line here and describe this. Force in the UV plane. But really it can be a force in space. But I'm just saying the UV plane because this is going to be easier for you to think about. Then I can take and shoot I can find the point where this is perpendicular to O. The shortest distance from O to here is going to be that perpendicular line, and I can take the magnitude of that force, of course, and multiply it by that distance, and I have a moment about O, right? Well, we can take this force, now let me call it an F for a force, and I can cross it with a position vector that originates from O, the point that I want to get the moment about, and heads out here to this force. And now I can take that to find my moment about O. I can take that R and I can cross it with F. And when I do that, I get my moment, which is in a different direction, but it's a direction that is perpendicular to both vectors. It's not in that direction, but it will head in a direction that heads perpendicular to all these, kind of like a z direction. If u was x and v was, if v was x and u was y, I say this is z. And this will be my moment. And this works because essentially we are taking into account this angle theta and that distance d. And if you recall that the moment about O should be F in this situation times R, or written in terms of these things, the moment in vectors should be F magnitude R magnitude times opposite over adjacent is D. So F R sine of theta. So this is actually like representing D, and this is R magnitude F. So that's going to give us a moment. But to convert it into a vector, we need to use a unit vector in the, well, UV, I guess if we're doing these things general, we'll call this a W, unit vector in the W direction. I don't know why I just didn't call this X, Y, and X, Y, and Z, but it is what it is. Works just as well. And notice that vector is perpendicular to both of these vectors, F and R. So why is this R cross V? Well, think about it this way. This thing intersects R here. No matter where we drew it, it's going to intersect R somewhere. And this vector continues on in this direction. And use your right hand rule. If you cross this way, you're going to end up with a positive. Your thumb's going to point up. So if your fingers are facing this way, your thumb is up here. Now you close your hand and your fingers are sort of rotating towards F. Again, your thumb is still going to be pointed up. So that produces the direction of our vector. If we did, yeah. This approach works regardless of where we place R. Doesn't matter how we draw our R, as long as our position vector starts at our place where we want to do our moment and ends touching our force, we are in business. So the moment about O equals, put some ones, twos, threes, equals R1 cross F, and equals exactly R2 cross F equals R3 cross F. And we just got to make sure we follow our right hand rule convention. Now, there is something I don't think I mentioned, and that is that when we're talking theta here. This theta is the angle between the tails of, it's going to be the angle between the tails of R and F. So when we cross here, that's going to be the tail. This is the angle theta. And the same deal here. And theta is, so I'll put a note here. Note theta is angle between tails of vectors. One bullet point. The other bullet point is 0 is less than equal to theta is less than equal to 180 degrees. So in 3 space, we can do this as R cross F, and again, equals the determinant of this, which means that MO equals this result. So you can memorize this if you want, but I don't think there's any point. It's easy enough to derive it when you need it. Let's do an example. All right, here's our example. We're pulling on this tower with a force of 2 kilonewtons. 2 kilonewtons. Tower's 12 meters tall. The point here where we're standing and pulling this rope is 12 meters in this direction, 4 meters in this direction. Let's go ahead and find the moment about O here that force is creating. Okay, so the moment about O is going to equal some position vector cross our force. So the question is, what do we want to choose as a position vector? Well, we could choose a position vector that comes out this direction. That would touch our force. We could also choose a position vector that comes here. If we could figure that out, that would be almost impossible to figure out. But any position vector that touches our force, the line of action of our force, is allowed. This is the most obvious one, and that, so let's say choose R equals, if we went from 0, went from here, it would be, I think it's going to be better if we make this our origin up here though. So if I make my origin the top instead of the bottom, even though my axes I'll put up here, even though we're trying to find the moment about this point here, this is probably going to be easier for us. So this is Y, this is X, and Z is in this direction. So if I did that, we would have a position vector of for I plus 12J minus 12Z. Yeah. But look here. I can go from here to up there. I can go from O to this origin point up here. And I can say R then equals, or actually our position vector, we need to start from O here. Since by definition we need to shoot, if we're going to take our moment about O, we need to shoot the position vector from O. So from O, our position vector actually is 4I 12J. But here from O, a position vector that touches this line of action is actually shorter we could use. And it's just up the z-axis. So this is 12K. So even though I've moved our axes up here, I can see that to shoot a position vector to this point from up here is minus 12. That would put the vector in this direction, and we need the opposite of that. So we need a negative of 12, which is positive 12. Added some letters, so now we have a unit vector here, and here's the vector. Here's the determinant I must solve. Recall these lines for the signs of our cofactor. This will be my first term. That's my second term. And here's my third term. And here's my final answer. Notice by solving the determinant this way, I only really had to do this one term. That's all I have time for. Notice there's no z component to the moment. It acts only in the x, y plane, perpendicular to R and B.